Okay, so good morning, good afternoon, and good evening. Welcome to this Multimodal Beam Prediction Challenge 2022. I am very delighted to welcome every one of you that's joining the call today to this presentation. And I would like to welcome also the teams that have made sure that submitted the solutions to this problem statement, to this challenge, and are here to do their presentations. So at this point in time, I would like first and foremost just to do a few introduction from my side. Reinhard is not joining yet, so I can do the quick intro of the session, and then I'll give the floor to Professor Ahmed, and then we can go to the teams. So what I would like to show or inform everyone is the statistics that we have received so far in this problem statement. We had 55 teams that registered to participate in the challenge, and these 55 teams comprised of about 104 participants. And out of these 55 teams, we have received 13 varied submissions from teams. Of course, we had more than 120 submissions because teams were allowed to submit multiple times. But overall, we had submissions from 13 teams, and we have provisional ranking of all the solutions for this problem statement. And I'm delighted that I believe that the solutions that have been received, or the scores are state of the art in this field. So thank you everyone for making time, for making sure that you submit varied submissions, varied solutions, which are really pushing the research in this field. Thank you very much. At this point, I would like to welcome Professor Ahmed, who is the Assistant Professor at the School of Electrical and Computer Engineering at the Arizona State University. Welcome, Prof, and the floor is yours for opening remarks.
Thank you. Thank you very much, Thomas. So, yeah, I would like also to start by thank you for all the teams that participated in the competition, and thank you everyone for attending. This is very exciting, I think, competition, and also very exciting to finally see some more details about the proposed solutions and the results. So as you know, who were at least following the competition, so the main motivation starts from the challenges that the key trends and communication systems impose, like when we go to higher antenna regimes or higher frequency bands, then we start getting these high data rates, but then we have a lot of challenges with training overhead, beam training overhead, channel estimation overhead, the difficulty in supporting mobility, low latency, reliability, and energy efficiency, and multimodal sensing of the environment. So having this perception of the environment geometry using various sensors, from wireless receivers as sensors to all kinds of sensors and visual sensors, radar, LiDAR, position, cameras, and so on. So all these different sorts of sensors, they provide a lot of information that could potentially build this perception to the network and help the network make decisions, help the network and the device, of course, make decisions on many things, like from beam alignment to blockage prediction to maybe positioning to handoff, user scheduling, codebook design, and many more. So so now, in order to make really any real progress in these ideas, especially with machine and deep learning, we need data sets, and that was the motivation behind DeepSense 6G dataset. And in this in this competition, particularly interested in taking this one step further towards really examining how and testing the potential of these solutions and these ideas in general. And to do that, we need to validate two things. First, we need to see how these solutions perform on realistic data. So not just real data, but also realistic realistic scenarios and measurements that are taken from realistic scenarios. So normal, let's say in vehicular applications, so normal scenarios where there are vehicles, there are other objects moving in the streets and so on. And then another also important aspect is the ability to generalize to unseen data. And these were the two main questions that that this competition was designed to bring some insights and to motivate and really see how far we can go and how accurate these algorithms could be. So this framed the problem definition and the data set collection and how we kind of pose the full problem. Very excited that we have at least more than 13 teams participating and finishing all the way to the end and developing algorithms and obtaining some very interesting results. Very excited about results and the performance that's really showing potential. And yeah, maybe I will stop here and we'll let the teams start presenting their solutions.
Okay, thank you so much for the words. And instead of Reinhard, I have Vishnu. Maybe Vishnu can give a few remarks and then we can ask the teams to present. So after Vishnu presentation, we are going to go to the first team, which is Avatar. So Maximilian, you can maybe start preparing. So Vishnu, please.
All right. Thanks a lot, Thomas, and thank you, Ahmed. I was just while you were talking, I was remembering our first talk, and the way we have come through is amazing. It's just amazing. I think the data set what we had discussed, Deep Sense, at that time when we were discussing for the first time, I remember that you had everything pretty much set up. I mean, the data set was there, the papers, the reference papers were there, and there were some ideas that you had as well. So I think it was just the perfect timing for us to collaborate. And we had, I think, looking at I was listening to Thomas about the number of teams as well as the number of solutions is just amazing. I think the type of data which you had, the type of problem statement that you had, especially as you mentioned just now, the multimodal data and the fusion that you had with the different characteristics of data. That's just, and how it behaves. I'm very curious to find how the teams have really solved that problem. And I think as you pointed out in our very first talk, I think there is a lot of future opportunities to look at as well beyond these things. With that, my curiosity gets better of me. I would like to welcome all of you to this competition. You're in great hands. I think Ahmed is the best person to take this. There is a very extensive research behind this. So we are very happy to collaborate. Thank you very much, and good luck for the teams.
Thank you, Vishnu. And now we are going to dive deep into the discussion, into the solutions that have been proposed by the teams. So each team has 10 minutes to do their presentation, and hopefully we can have 1 or 2 minutes for Q&A. So first and foremost, we give to Team Avatar. So good afternoon, Maximilian.
Hello, thank you. I cannot start screen sharing while the other participant is sharing. Thank you. So let me share this. So you should be able to see the screen. Okay. So, okay, great. So thank you for this interesting challenge. I took upon me to try out a lot of different things, and I'm happy to show you what I found. And there's a lot of more questions that came up after doing this challenge than I had before. So that's normally a good thing, I think. So let's go quickly, as you all know more, I guess, than me onto this data set. I just give you a run through my thoughts, what I wanted to do. So at the beginning, I said, okay, this should be more or less a line of sight challenge because millimeter wave propagates very nicely in line of sight condition. But since it's a sequence, it's also beam prediction, so update challenge. So at the beginning, I said, okay, what are these different sensors and what are the different modalities and what are their local coordinate systems? So I had a look at the camera, see if I can see the car with a GPS antenna on it. I looked at the radar and tried to cross-section visually, so eyeballing, seeing, oh, when does this make sense and when it doesn't make sense, then the LiDAR and GPS data. So at the end, I figured some things out. So that the camera and the radar are really perfectly aligned, meaning they're both looking at the center at the same position and the same angle, so they are directly correspondent. So if I now look at the LiDAR, it turns out that I need to find the mean angle in which direction that I get the center again. So I need to rotate this. So I did the first rotation based on some form of estimation. Same for the GPS. So I was looking into saying, okay, GPS is a global system. I want to have it locally because I want to have the direct correspondence between GPS in a generalized way to my beam index. So I needed a quick calibration. So which I did is I looked at the car mounted with the GPS, looked at the GPS antenna and said, okay, if the GPS antenna with a visual correlator is at the center pixel of my image, I use this GPS position as my center position and then calibrate my angle based on this. So I effectively rescaled everything in the GPS and did some pre-data clearance for me because I thought, okay, garbage in, garbage out wouldn't be nice for me. So I wanted to make sure that they are perfectly aligned together in the same local coordinate system. So the idea was, okay, I check as well at the data diversity, can I exploit some form of, okay, there's more angles there, there's a certain range there. It turns out the data set is quite diverse and it's diverse enough so I cannot do anything manually and I really should use a neural network. So moving on a little bit, I wanted to understand how good and how mobile is the car. And therefore, I did a eyeballing inspection of the most large scenario and said, okay, to myself, the angle based on my calibration of the GPS, I plot in an area fashion, and then I plot the beam index over the area as well, because I have the GPS position and mark my base station. And what I found is the direct correspondence between the angle and the beam index in most of the areas, which is to be expected because it should, if the car stands still, it should be the same beam index, which is another validation of my approach. And I wanted to be better than the classical line of sight estimation. But to define the classical line of sight estimation, I went ahead and said, okay, I use a least square solution. I just said, okay, I have my angle calibrated. I use a form of function optimizer and said, okay, after the 10th polynomial order, I look how does these coefficient look like. And it turns out that if I have, let's say, only a line of sight, the GPS and no mobility, I have almost a linear function because already this alpha is the input angle in radians. So this is very, very small, the first two, and only the last two values give a shift and a smearing of the correspondence between the beam index and the input angle calibrated on the GPS. And it turns out that this solution is also quite good in a generalization. It's not very good, but it gives already reasonable results. So that was the measure for me to say, okay, where can I enhance on? Where can I beat this? So therefore, I looked at BeamBench. So I just called a framework where I coded up all different variants of it. I coded up autoencoders, contrastive learning, supervised on feature extraction, wanted to understand, does it make sense to use, for example, the enormous advantages that vision guys did in predicting bounding boxes and so on. Can I just use bounding boxes to go down to the beam index? So I did a large amount of direct approaches saying, okay, I just take the last data index, and I looked at also at the LSTM versions where I tried to do this beam tracking. As it turns out for myself, I didn't read close enough, at least this is what I believe, is that the data in the training and the testing have different sampling sizes, making my sequence approaches very, very bad. They were very, very, very good, better than the direct approaches in the original training set and in the adaptation data set for given scenarios, but in the unseen, it was not that great. Meaning for me, I at least understood that for me, LSTM needs a fixed sampling grid and is not allowed to change between sampling sizes and measurement, which makes it a little bit susceptible to errors, but might be to go ahead and move to some form of transformers in this case, but I didn't have time to do this. So I went ahead and looked at the approaches and wanted to understand what did I learn and what areas did I improve on. So effectively, I plotted the DBA score over the area and saw, okay, where are each solutions weaknesses. So I plotted the classical, which has its weaknesses in areas which is very, very close to the base station. I guess this is due to the high mobility based on being very close. A radial component is then stronger. And the same holds for all these three data sets. And then I wanted to see, okay, can I make a neural network do this tracking better than the classical solution? I will skip these two solutions because I don't have that much of a time, but let's go to the last solution that is a good trade-off, at least for me. So if you would predict, use a camera autoencoder, go down to the latent space, combine and regularize the latent space with your GPS position, and then do a downstream task, you can get away with, let's say, a better solution, which is more spatially equally performing. And this is what we see here as well. So it is learning to generalize. It moves very well to unseen scenarios, although the car type was completely different. This was a green car and not a silver car in the other data set. But it learns the general function because you regularize it with the GPS position. So I looked at then the data statistic bus area was giving me one thing, and I wanted to see what is the effect if I do now this adaptation. And the idea was that, okay, now I look at the original solution, which are the bold curves and the adaptation after. Does this help? Or does it make it worse? Because if you could overfit and so on the adaptation data set. So I wanted to see the gains if I do it correctly. And what it turns out in the scenario 32 and 33 and 34, if I just look at the more evolved solutions and not only the simple solution, I see they're exactly the same. So the adaptation data set didn't help there. So I already have a solution for this data set. In the case of the completely unseen data set, the story is completely different. So I had not a generalized solution. I had a solution which was working for these three different data sets, which is okay, which would be in a large data set a reasonable solution. But in this case, it was not good enough. So then I said, okay, let's take a look at a more advanced solution where you can see here in this one, if you do this adaptation data set and just train the adaptation on these two more advanced solutions, you can get very, very close to the classical solution, even beating it in most of the cases in higher region of the CDF. And therefore, I turned out this was my final solution to the dataset competition. So I handed in these combination, and it turned out that all of them are quite close because all of this GPS regularization gives you a lot of information. But from my understanding is that the camera was the main driver with GPS to give the most robust and diverse solution. Thank you very much for your attention. So I think 10 minutes was it.
Thank you very much. Probably we can get one or two questions. I see a hand up from Anastasio.
Yes. Hello, Maximilian. Thank you for the interesting presentation and the approach. I just have one question. So did you use scenario 31 for your training, or you just use it for evaluating afterwards?
So scenario 31 was the complete unseen scenario besides, I think 50 or 25, I think 50 data points which I was given. And this was the results. I used these 50 data points to adapt to this data set. This is the only training on scenario 31 which I could do.
Okay, so to understand, so you did training on just 50 points of the scenario 31.
So the idea is you train on all these 32, 33, 34. And get your weights out, and then I just use a limited learning rate and a limited regularization in sense that I just then adapt to this, saying, okay, here's a new scenario, please give me a better solution. So the weights where I looked at the weights, it's slightly changed, but I just need a form of fine-tuning or few shot adaptation, if you want to call it like this.
Okay, thank you.
Okay, thank you. We have another mic open from Kian. Do you have a question?
Yes, just a question. Hi, Maxim. Very nice to hear you. Just wondering, did you use LiDAR or radar data, or as you show the solutions mainly on just use a camera and the GPS?
I effectively tried everything out for a direct approach. I tried radar is in a dense form, meaning I used CFAR on it, did only take the peaks out of it. I used autoencoders on radar, autoencoders on camera, autoencoders on LiDAR, going down to the latent space and then downstreaming this task to get the beam index. I try to make all the combinations, what I know of state of the art, and try to benchmark them each other. So I tried every combination from these things. It turns out if you increase the data modalities, the sensor modalities, you get a better solution. But the difference, at least for my results, were that going with the full-blown all-day radar LiDAR was not that huge of a gain compared to just going camera and GPS only.
Thank you so much.
Okay, thank you very much, Maximilian, for the presentation. Now we go to the next team that is waiting, and this is team TII. So Tiang, are you connected?
Yes, yes, I'm connected. Can you hear me? Yes,
so you can share the screen.
Yeah, I can share the screen, right? Okay. Can you see my slides?
Yes.
You can see my slides.
Yes,
right?
You can start the presentation.
Okay, yeah. So hello everyone. We are a team from the TII Technology Innovation Institute. We have 4 researchers participating in this. So we're happy to present, to share with you, talk with you our solution. So I'll jump directly to what the key issues we find actually. So we find that from the data sets, first, if we use the camera's images, that we have some scenario which is nice scenario 33 and 34, which we find it really hard to actually identify the objects. And also because the image contains multiple objects, it's really, we don't have a labeling or which object is actually our users. And we go directly to a fusion, but the problem is that fusion of the 3D point clouds to the image and radar and 1D GPS, it's a bit challenging, especially when you, how do you want to make all these different dimensions of data on the same plane together. And the huge data imbalance, as everyone see, the scenario 31 is quite small, like 50 samples, and but it occupies a lot in the test data set. And this brings us to a domain adaptation problem, as in machine learning, many that especially the test data set have different sampling rates compared to the training data sets. And so this means we think based on the statistical learning, this really, we cannot attach really a true generalization. The best thing is if we can learn the structure of the data, that on a latent space, you're not really getting into the raw data into the deep learning if we also use, but rather if we can create a structure of the data and then learn how this modality can be correlated, that would be more towards a truly generalization. But adapting to our time, actually, we go directly into deep learning, and we use this neural network structure. Actually, originally, this structure actually was a fusion of the image and LiDAR data they use called transducer used for autonomous driving. We extending these and then adapting these more to our scenarios. Basically, also we adding some of the data augmentation enhancement on top of it. Basically, we use the image data. For example, we have all the you have several sequence of the image go into a mirror net. We use for enhancing the image. So in the night scenario, enhancing to brighten it, and this go to into a ResNet. And each of the convolutional layers will get you the features from the images. And the LiDAR, we put it, first we use a projection, putting the 3D LiDAR. Actually, we are setting a threshold that we project it into the 2D, making a bird's eye view of the LiDAR, and also go to the same of the ResNet. And for this LiDAR, actually, we are basing on one of the solutions that you have before using the FFT. But what's the differences is that we're combining the velocity and the angle, creating a map of the range angle velocity, and then feed into again the ResNets. And from the GPS, we do an embedding. We create an embedding layer using the MLP, and then using to learn basically like making the two vector GPS into a matrix. And all these will get into the transformer. Basically, we expect the attention layer to learn the correlation between these modalities, and then to forward into the next convolution that each of these going forward will have the features from the previous layer, and then go into MLP layer to create the beam index 64 beam index. But the problem is, okay, the way we train is that, okay, we separate the data sets, we combine the development adaptation, we use some data augmentation, which we'll brief later, and combining them and randomly split to 90% of training, 10% of validation. First, we do some soft targets, which means we don't use the hard targets of the beam index, but instead we create a Gaussian distribution based on the best beam and the neighboring 3 to 5 beams, because this affects, we find affects more, reflecting more better the DBA score calculation. And we adapt the focal loss on it, because I see we have a huge data imbalance. So the focal loss will let you to the learning training process to focus on those hard examples. Especially we find that scenario 31, the confidence is quite low. So using these that we not get the average loss of all the samples, but the loss will be more on the scenario 31. And we do a cosine decay of the learning rate to control it to be better of converge rather than fluctuating in the later. And then we use these exponential moving average, which means the best model we take is storing the last n steps rather than getting the instant stops of the model weights. We also test some semi-supervised learning based on fixed match when we try to create some pseudo labels from the test data set and based on the augmentations of the data. But this actually, we have found actually these things, the last two actually not actually enhanced much, mainly on the, because the problem of augmentation we'll talk later. So data pre-processing, we do, as we say, we use mirror net to get image in the night scenario to be brighter. And we use the semantic segmentations of the objects in the day scenarios. So this inspires us to better classify the objects, especially the moving objects. And from the point cloud, we first use a bird's eye view, converting the point cloud 3D to 2D. And then we use the adjusting the field of view. Actually, as Maxime also say, we find that the LiDAR angle is different from the camera angle. So basically, based on view, we adjust making the two, the point cloud and image on the same angle of the view. And we also test to filter the background objects. Basically, we calculate the differences of all the LiDAR samples, and then we fill out all the backgrounds of the buildings, trees, and keeping only those moving objects like the cars and the pedestrians inside the LiDAR, inside the point cloud. For the radar, we combine the angle and the velocity. GPS, as I said, we calculate the reference to the base stations. So this is the effect of after pre-processing. As we said, we brighten the image, we do the point cloud to filter the background and using the radar velocity and angle. And we also do some data augmentation, but in fact, this augmentation doesn't actually help us a lot. Because the reason we use one is we want to generate more of the data from scenario 31 as given from those, especially these 50 samples. We use some traditional augmentation on the image, like taking the brightness, contrast, saturation, and from the point cloud, we do some down sampling and adding some small noises, and radar also adding noise in the spectral domain. We try to create more of the data, like each of them 8 times, 3 times, 2 times, like 48 times of the data, to be able to allow us to do some more training, a balance of data sets in all the scenario. This is performance we found. Actually, we show you all these actually. So from the beginning, we just use one-time steps with our softened targets, and we find what's improving. Most of the improving is that we put in more of the time steps. It improves, of course, improves a lot, but also on the focal loss we add, which solves the data imbalance problems with this improving a lot of performances. Here, okay, we are mixing the adaptation data set. This gets us better. And finally, we say we found that when we adjusting the LiDAR's field of view to be aligned with the camera, this actually improves us a lot. And this is the best scores that we get from here, that our training and DBA scores that we look like. The other techniques which we're presenting to you, actually, we all integrated here, but actually those especially these are actually the main improvements we can conclude from here. So I guess that's all. Thanks a lot. Happy to exchange with you.
Thank you so much for the presentation, and I'll open for Q&A. If there is anyone who has questions, you can open your microphone and ask.
Hello. Hello, thank you for your presentation. Congratulations for your solution. I have a question regarding the pre-processing of the camera data, and in particular regarding the enhancement network, MIRNet. So how the training of this network took place?
Well, this is actually, it's actually state of the art. It's a pre-trained model. Actually, we just use it from the pre-trained model and to directly use it to do the enhancement. Basically, from the reference, I think it's from this paper, the low light image enhancement. I think this is it's actually integrated into
Okay, thank you. So it was trained on samples, not from this data set, from an external data.
No, not from this data. Trained on, I mean, from computation, they train from large number of samples from other images, general images.
Thank you.
Thank you.
I would have another question. I thought as well on doing some sort of pseudo labeling. Did you get further of pseudo labels? I didn't understand how to create a good pseudo label for the beam.
Yeah, basically the fixed match is the way. So you train on you do supervised learning as you usually do, and then every iteration you train the model, and then you use the model to use the test data set to get input, and then you will get a confidence, right? Because after the output you will get a confidence, and basically this method is that you select the high confidence. And then you think the high confidence, okay, the high confidence, the output, they are pick an assumption those are the right outputs, and you trust them, and then you create an augmentation of the test data. Basically, you have the differences. So they are the same sample, but they have the data has differences based on the augmentations, and then you use it to approximate the high confidence labels that you've got.
Yeah, makes sense. Thank you.
Yeah, thank you.
Thank you so much. I believe that we can go to the next presentation. Yep. So thanks, Team TII, for the presentation. Last call for Team MMJ. We haven't received any response from this team. I believe that Team MMJ is not here. So we are going to skip them, and we are going to go to the next team. 805 Mainstream, are you here?
Yeah, hello,
okay.
Can you see my screen?
Yes.
Hello. Nice to meet you all. Okay, now should be full screen.
Yes.
Okay, my name is Matteo Nerini, and my team was composed by myself, Rafael, and Renke, and we are all PhD students at Imperial College, London. And this is our solution. So our solution is actually very minimal, that can be fully described in this slide. So regarding the input, we found beneficial to use only the camera data, so the RGB data. And we consider only the 5th sample in the data set, so the one at timestamp T. So we consider this 3-channel image with this dimensionality. So as a pre-processing, we just downsample the image because we found the image had very high resolution. And so it was really computational expensive to process with the convolutional layers, the whole image. So that's why we reduced the dimensionality of the image without losing actually semantic meaning, because the cars and the objects were still visible. Then we process our image with the 4 convolutional layers, and we apply ReLU activation function, batch normalization. And this is our feature extraction process. And finally, we classify the image through 2 fully connected layers, and we have the predicted beam. So our network was trained in a supervised way, and the training set was composed by the whole development plus the adaptation dataset. In this regard, we found fundamental to train also in the adaptation dataset, because without the 50 samples of scenario 31, the performance on scenario 31 was nearly 0. But with those 50 samples, we could reach a DBI score of 0.4 in scenario 31. And we trained the network with a batch size of 32 for 25 epochs with the Adam optimizer and a learning rate of 0.01. And of course, the loss function was the cross entropy between the output and the optimal, the ground truth beam, the one hot encoding of the beam. And this was our final performance on the test set. Thank you.
Thank you very much. That was really brief and interesting. Do we have questions from the audience? So maybe I can start from myself. In this case, you proposed to use the camera data only. So in terms of fusion, if you have you tried other approaches, and how better or how poor were they performing? And in this simplified case, in terms of training, how much was the acceleration in terms of training time? And
yeah, thank you for your question. Very relevant. Actually, this was the first solution we tried. I would say the most basic solution one could try. And actually, then we tried a lot of other solutions, trying to fusing all the modalities available. but actually the performance was not improving. The computational complexity, so the time required for the training, was increasing a lot, but not the performance. So our explanation was the following. So modality fusion is particularly useful when the estimations from the different classifiers are nearly independent. In our case, we found instead that the samples that were wrongly classified were always the same, with the camera data, considering camera data, considering LiDAR or radar, most probably because our wrong pre-processing strategies, because we were happy to see that the first teams actually got a benefit by fusing several modalities. But yeah, in our case, we found more beneficial just to consider camera data, because we couldn't see a performance improvement, only a computational complexity improvement.
Hello.
Hello.
Can I make a question too? Maybe.
Sure.
Yes, please.
So you mentioned that you are using only RGB data for classifying the beam index.
Yeah.
But in some scenarios we have multiple cars and some samples in the RGB it does not specify which car we want to track. So we need the GPS information in order to know that we need to track the specific car.
Yeah.
So maybe your solution works well for scenes that does not have many cars. Let's say it's only one car and we need to track this one.
Yeah, you're perfectly right. So, and also we noticed that our solution may be misleaded by some pedestrians. In some scenario, we had some pedestrians close to the base station or the camera that were a huge object passing by, which was not our receiver, so a distracting object. Yeah, in this regard, we found, we tried also some solutions from applying transfer learning, so to trying to detect always the same car. And these solutions came from very famous networks used in computer vision, but that unfortunately had to be pre-trained. And it was according to the rules of the challenge, if I'm not wrong, that we had to train our architecture only with data taken from these data sets. So actually we discarded all the solutions that we tried employing a sort of transfer learning. But yeah, you're completely right. So considering only RGB data, we are misled by the big objects, the other cars that are not the receiver.
Okay, thank you.
Thank you.
Okay, thank you very much for the presentation. Last but not least, we have Team Utimo. I'm not sure if I am pronouncing well. So Antonio,
hello.
the floor is yours.
Nice to meet you all. Can you hear me well?
Yes.
Okay, please give me some time to share my screen. You can see, right? Okay. So our team, Ultimo team, is composed from Dimitrios Tsitsiris, Anastasios Vafiadis, Alexandros Papadopoulos, and myself. We are from Visual Analytics Laboratory, Information Technology Institute, from CERT for Risk and Technology Hellas, located in Thessaloniki, Greece. The outline of the presentation is a brief introduction about our organization, motivation and objective, preprocessing, network architecture, results of the overall approach, and finally some conclusion and future work. So CERT ITI is active in different Horizon Europe projects related to artificial intelligence, data fusion, counter UAV, cybersecurity, and autonomous vehicles. You can find more details on these links. The technologies areas is related to IoT, 5G, 6G networks, neuromorphic computer, photonics, reconfigurable intelligent surfaces, and other domains. I'm not going to stay so much on this. So I'll give my floor to my colleague, Dimitrios Tsitsiris, who is going to present in more detail the technical solution of our team.
Hello, everyone. The motivation and the objective of this problem is the beam prediction using higher frequency bands that adds an overhead in the training process at the transmitter and the receiver, and the sensing aided beam prediction that is a promising solution since the sensor data collected by the RGB, LIDAR, radars, GPS receivers, etc. can enable can help us decide on where to point their beams. So the problem is the beam classification and actually to predict the optimal beam index at the specific time. We were given a multimodal training dataset that consisting of data collected at different locations with diverse environmental features and distractions in order to develop machine learning models that can adapt and perform accurate sensing aiding beam prediction at an entirely new location. So this is an overview of the data we were given. It's actually CSV files that contain the sensor file names for each scenario. The data were already pre-processed and aligned in time. So we have different modalities, the RGB modality, the radar, LIDAR, GPS. Actually, the GPS modality had also information about the base station, the stationary station, and also a unit 2 deployed, a unit 1 deployed on a car that gives us 2 specific locations in each sample. Also, in the training only dataset, we were giving wave information that the sensor received from the car. So in terms of pre-processing, the GPS data were converted from decimal degrees to Cartesian coords. So actually we performed the conversion, and furthermore we added random noise in order to perform augmentation of these positions to the unit 1 only. Also, as a feature, we calculated the distance between the unit 1, which is a target, the car, and the unit 2, which is the base station. Also, we are using RGB data because the resolution was very high. We downscaled to 480 by 270 resolution, and we performed normalization to 0 to 1 by dividing with 255, which is a maximum pixel value. Also, for the radar data, we calculated with Fourier transforms the range angle maps and range velocity maps, as we can see in the images below. Now, about the network architecture, we performed late fusion, and that means that we were processing each modality and then extracted features that were added on a GRU layer. And for that, for the GPS input, we used only a GRU for the feature extraction. For the RGB input, we used a pre-trained on ImageNet DenseNet for each one of the 5 images. So we performed feature extraction on a sequence and then used global pooling in order to flatten those features. Also, we used an efficient net, also pre-trained on ImageNet, in order to extract features from the radar angle and radar velocity in the same way. All the information, all the features were passed on a GRU and passed into a full connected layer. So for the training, we split the dataset into 80/20 train test split ratio. We used categorical cross entropy loss. Also, we used Adam optimizer and 25 epochs for the training. The metrics for the training for the categorical accuracy is the top 1, top 3, and top 5. And the only way to exploit the MM wave probabilities that we were given in the training dataset were used for label smoothing. So the target is not 0 and 1, but contains probabilities given to us by the MM wave receiver. Also, in our data loader, we used a cache in order to cache plots produced by the radar and improve the training performance after the first epoch. So here we can see the training and validation loss per epoch. I think it reached a point that overfits, and we stopped training just before the epoch 25. Also, the results on training on the 80% of the dataset that gives us about 50% top 1 accuracy and 94% top 5 accuracy. The validation results on 20% of the dataset, it's a bit lower at 43% top 1 and almost 90% at top 5 accuracy. So our approach achieved about 55% overall DBA score. We can see the analysis of the scores in the table below. As we can see, the scenario 31 was the most difficult for our model to predict. And that's because we were not using any data from the scenario 31. Also, the RGB data improved the generalization of our model and increased the performance on the scenario 31, but the radar data provided little to no benefit using this model architecture. So for the future, we plan to improve the network architecture in order to exploit benefits from the radar modality. Also, we did not use any LiDAR information that could also provide a significant boost, and maybe a better fusion approach in order to enhance the accuracy of the model.
So thank you very much for your attention. We are open to collaboration. I mean, apart from this challenge, it was a very good opportunity. It was very interesting for us, and we're open for collaboration afterwards as well. Thank you very much.
Thank you very much for the interesting presentation, and I'm going to open the floor for Q&A. So if there is anyone who has some questions, please.
Yeah, I have a question.
Yes, go ahead, please.
Yeah, so just wanted to ask if you used any technique to handle the imbalance data set. You know, every beam had a different amount of data for present in the training data set. So if you did anything for that.
Yes, regarding the imbalanced data, what we did is that we used a stratified k-fold split, which allowed to have a correct distribution between the train and the validation set, and we used like 5 folds of the stratified split. And these are the results reported in an average after the 5 folds.
Okay, all right.
Do we have...
Hi, I have a question.
Hi, Rafael.
Yeah.
Yes, please.
Hi, I have a question. Thank you for your presentation. In your late fusion stage, you mentioned that you use pre-training and DenseNet 121 and EfficientNet P0. Were these also pre-trained using other data from outside sources?
The pre-trained one means that they were on just the weights from the ImageNet. So when loading it, let's say in PyTorch, we just activate the weights from ImageNet. It's not like from data that it's completely irrelevant to it's not like external data that we used for this challenge.
Oh, but they were built-in functions in PyTorch then?
Yes.
Okay.
Okay, thank you very much for the presentation. At this point in time, I would like to go to the next agenda since we are running out of time.
So may I ask a general question if possible?
Yes, please.
Yeah. Was it possible to use data from scenario 31 as well during the training procedure?
Professor Ahmed? Or...
Yeah. You mean like whether it was allowed or not?
Yes, because we didn't use any data from scenario 31, and we just wonder whether we could use this could boost our performance. This is why we're wondering.
Yeah. So we shared only like a very small data set of 50 samples of scenario 31, right? And I think the objective was mainly that, okay, this small data set can also help in adaptation. So yeah, so we shared this data, and yeah, it was fine if you would like to use it for training as well.
Okay, so with that, I would like to move to the next session. So I give the floor to Professor Ahmed to announce the awards and then offer some closing remarks.
Right, so let me try to share. So
okay.
yeah, I'm trying to share the screen. Okay, now. Right, you see the screen?
Yes.
Okay, perfect. All right, so thank you everyone again for joining us, and thanks for thank you to the teams for participating in this competition. So this is a summary of the results we got for the first top 5 teams. So this is basically the results. These are the results for scenario 1, 31, 32, 33, 34, and combined. And this is combined based on the ratio or the weights of the different scenarios that we have in the test definition, in the ranking and the evaluation definition. All right, so that was the ranking of the first top 5 teams. Avatar first, TII second, MMJ third, 805 mainstream fourth, and Altmo, I think, fifth. So you all did really great work, and these are really exciting results. For the winners, so I'm happy to announce first place Avatar, total DBA score of 71.71 or 71%, and second place TII of more than 66% DBA score. For the third place, we are still verifying and validating the code. So once we finish, there are some delays from the third team. So once we finish the validation, then we'll announce either the third place, basically MMJ, or 805 mainstream. So one of them will be the third winner. So we're sorry that we are not ready yet to announce the third winner, but hopefully we'll do that soon. So with that, congratulations to the winners, and congratulations also to the top 5 teams, and congratulations, I think, to all the teams that really participated actively in this competition. You'd like to thank you again very much, and thanks to everyone who attended today. And I also would like to thank my co-organizers from Qualcomm, Arash and Hamid, and from my group, my PhD students, Goranj, Ahmed, and Joao. And I think this is just the beginning of many more research directions to explore, and even in this specific machine learning task of beam prediction, as you see, the first place or the top score, even though it's really very exciting, but still 71%. So we have a long road to go, and to really make these solutions applicable to and deployable, hopefully, in real world systems. So that's, I think, very exciting, and triggers and encourages more and more research. I also would like to thank Qualcomm for sponsoring this competition, and for encouraging this research. Yeah, I think with that, can back to Thomas, and if you would like to.
Yes, thank you very much. I would like to maybe ask a few participants, the teams that have participated in this competition, in this problem statement, to give a feedback, some maybe few words. How was your experience? Was it too difficult, or was it easy? Like just general observation that maybe we can consider it for the next iteration of the challenge. So I open the floor to anyone who has participated in this problem statement to give some feedback.